Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hello and welcome to episode 117 of the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. I am Tim Robertson, the host of the Observer's Notebook and also the coordinator of the training program within the ALPO. Thanks for downloading and listening. The Association of Lunar and Planetary collects and analyzes observations of various solar system bodies and associated phenomenon, and publishes detailed reports concerning these bodies in its quarterly publication, the Journal of the Association of Lunar and Planetary Observers, also known as a Strolling Astronomer. This podcast depends upon donations from you, yes, you, our listeners, to keep it alive. If you do enjoy what you hear in the podcast, please consider contributing to it via Patreon. You can give as little as $1 a month. If you feel even more generous, for $5 you receive early access to the podcast before it goes public. For a monthly donation of $10, you receive a copy of the Novice Observer's Handbook. And for $35 a month, you receive producer credits on the podcast. You can help us out by going to www.patreon, that's patreon.com/Observer's Notebook. And if you'd like to join the ALPO, you can for as little as $18 a year. You can find out more at www.alpo-astronomy.org. And you can also find us on Facebook. The ALPO, just search for ALPO Astronomy. And yes, the podcast also has a Facebook page as well. Just search for Observer's Notebook. If you enjoy what you hear, please subscribe. That way you'll never miss another episode of the podcast. Now, episode 117, and we're going to learn all about the upcoming mission of the James Webb Space Telescope. Sit back, relax, and enjoy. All right, I'd like to welcome everybody back to this edition of the Observer's Notebook podcast. Today we have a very special guest, Dr. Jonathan Gardner. He is the Deputy Senior Project Scientist for the James Webb Space Telescope, and also he serves as the Chief of the Laboratory of Observational Cosmology in the Astrophysics Science Division of NASA's Goddard Space Flight Center in Greenbelt, Maryland. Welcome to the podcast, Jonathan.
Thank you. I'm very happy to be here.
Yeah, it's good to have you. This is a very interesting topic. I mean, it's a long time coming for the JWST project.
That's right. Yes, we have been working on Webb since the mid-1990s, and I've been personally in my current position since 2002. So that is a long time. We're getting very close to launching later this year, and it's very exciting to be that close.
Yeah.
Ready for.
Now, this past 12 months, I'm sure has been challenging working in the COVID environment. What are some of the challenges and workarounds you guys have had to do?
So, first of all, personally, I've been working from home like a lot of the people who do desk work on the mission. But the hardware is in Los Angeles at the Northrop Grumman facility. And the hardware is in a clean room out there. And we have managed to continue to work on the hardware throughout the last year. There have been some impacts. While people are in the clean room itself, they wear masks normally, so that's no change. But the biggest impact has been going in and out of the clean room. That's a process that requires people to put on what they call the bunny suits, the white gowns, and put on their masks, cover up their shoes. This is all aimed at keeping the hardware clean, keeping it safe from dust accumulation. And the interesting thing is that the the biggest challenge in the COVID environment is just getting people in and out of the clean room. So as people are going in, normally you've got a changing room and there's multiple people in there. Right now we're going one at a time, and people go put on their gown and then they go into what's called an air shower that blasts them with air to brush off any dust they might have still on their gowns, and then they can go into the clean room. And we've had to cut that down to just one person at a time, and that has slowed things down a bit, but not too bad. We've managed to keep working throughout.
Yeah, I work in the clean room environment on the project I'm on through Goddard, and it's probably the safest place to be. Actually.
Yes, absolutely.
You're completely bunny suited up. You got a mask on all the time, and it's HEPA filtered air, so it's.
That's right. Yeah. So the people working in the clean room, they're not seeing a whole lot of difference, but like I said, the getting in and out has kind of become a bottleneck.
Right.
And also, especially right at first, having people fly across the country from Goddard in Maryland to the Northrop Grumman facility in the Los Angeles area, that was slowed down a bit as well. But as everybody, we're seeing the light at the end of the tunnel. People are starting to get vaccinated, and we're gearing up for shipping the observatory down to South America for the launch later this year.
Great. We'll talk more about that in a little bit. Now, are you guys allowed to travel? Because I know on our project, no one from Goddard can come out here.
It's very limited,
okay.
But there are people still managing to travel when that's really necessary.
Okay, great.
We have our meetings over virtually as well, like everybody else.
Right.
But when people actually need to be interacting with the hardware or observing delicate procedures, then they're able to go out.
Okay,
get
good.
Where they need to go.
So let's talk about your background and how you came to have your current position on this project.
Sure. So I'm a scientist. I'm an astronomer. I did my PhD at the University of Hawaii.
Oh, that's a nice location.
Yeah, it's a good place for ground-based astronomy, but I also always kind of was interested in space astronomy. From Hawaii, I got my PhD in 1992, and I went to England. I went to the University of Durham in the north of England to do research there as what's called a postdoctoral fellow. I was actually part of a NATO exchange program. And I was there for 4 years. And in 1996, I came to Goddard, where I currently work. I came there to work on research being done with the Hubble Space Telescope. That was I started just before the second servicing mission, when 2 new cameras were installed on Hubble, the Space Telescope imaging spectrograph and the near-infrared camera, which was called NICMOS. And with NICMOS in particular, it was a infrared camera working in the what's called the near-infrared, just a little bit beyond the wavelengths that we can see with visible light. And the research that I did was to do galaxy surveys. So essentially, we take the camera, we take Hubble, we point it at a part of the sky that we choose to be fairly typical, and we do the statistics of the kind of the galaxies that we see. So everywhere you point Hubble, it's sensitive enough, it's going to see lots of galaxies. And the more distant those galaxies are, the more time it's taken for the light to get from the galaxy to the telescope. And that means we're looking backwards in time to when the universe was younger. So this is the kind of research that I was working on, looking at how the population of galaxies change over time as the universe went from the Big Bang 13.8 billion years ago to the present day. And the research I did was in the infrared. And so shortly after I started working at Goddard, one of my colleagues mentioned to me in the hallway that NASA was starting to do a study about a new telescope that would be the successor to Hubble. And this successor telescope was designed in part to do infrared galaxy surveys. And I thought, wow, that sounds like the project I should get involved with.
Right up your alley.
I went along with him to a meeting, started to learn about the project. And over the course of the next few years, I started to help out with some research studies about what the telescope would look like, what kind of instruments, what kind of science program it should be designed to do. And then in 2002, I was invited to become the deputy senior project scientist on the project, working with Dr. John Mather, who's a Nobel laureate, who is the senior project scientist. So I've been there. I've been working on the project since 2002. Along the way, I also became the chief of the cosmology laboratory at Goddard, which means I'm kind of like a department chair at a university department, working with the other scientists.
So I take galaxies and the structure of galaxies and their formation is that's your area of expertise, actually.
That is, yeah. That's the research that I've done my whole career, and it's something that Webb is going to be very, very powerful at doing, although Webb is a general purpose observatory like Hubble, which means that it can do just about any kind of astronomy that you can think of. Just about anything in the sky, Webb will have something to say about it.
Well, then let's talk about the mission goals. I mean, obviously cosmology is a major part of that. What are some of the others?
So one of the first things I did when I joined the project was to work with a group of scientists that we call the Science Working Group to define the mission goals for Webb. And we came up with 4 science themes. The first science theme, which we call the end of the dark ages, the first galaxies, the first light, and what's called reionization. That is the very distant universe when we look backwards in time to within a few 100 million years of the Big Bang, and look for the first stars and galaxies that formed in the area that we're looking. In order to do this, we need to see things that are very faint because they are just so very far away. And when we tried to do this research with Hubble, obviously we learned a whole lot, but we didn't quite get to the point where we were seeing the very first galaxies that were forming. Hubble can see back to within the first 1 billion years of the history of the universe, back to less than 1 billion years after the Big Bang. But some of the galaxies that we see in observations like the Hubble Ultra Deep Field, the longest exposure that Hubble has made, the deepest, faintest picture that humanity has ever taken. Some of those galaxies that we see that are very right at the edge of what Hubble can see are still already a couple of 100 million years old. And that means that in order to see the first galaxies that formed, we need to go a bit beyond. So that actually defined the reason why Webb needs to be a bigger telescope than Hubble. It needs to be able to see fainter things and see further back. So that was one of the first defining goals of Webb. Another one is tracing those very first small pieces of galaxies over time, watching the evolution of the population of galaxies. And galaxies tend to evolve by merging together and building up over time into bigger and bigger structures. And so these first small pieces of galaxies will merge together and make the big galaxies like our own Milky Way that we see together. And over the course of those billions of years of evolution, the galaxies will go through multiple populations of stars and produce the heavy elements that eventually end up in stars like our own sun, which is a second generation star, and form the solar system and the planets in orbit around the stars. So that brings to the third theme, which is the formation of stars and their planetary systems. This is research that's mostly done within regions that are forming stars in our own galaxy, where we can see into the individual stars and the individual planetary systems being formed out of dust disks and clouds of gas and dust. And then the fourth theme is something that's become much more interesting and much more important to astronomy over the course of the last 20 years, and that is exoplanets. As well as planets in our own solar system. So it turns out that even though the original conception of the successor to Hubble was going to be something that would do galaxies and cosmology, it turns out that what we're building is going to be very interesting, very powerful at studying planets around other stars, and also studying the outer solar system of our own solar system, the outer planets. One of the things that has taught us an awful lot about extrasolar planets or exoplanets using Hubble is when the planet transits across the face of its host star. So essentially, this is just a chance geometrical alignment where the planet lines up between the star and the telescope. But when that happens, light from the star goes through the atmosphere of the planet, and the atmosphere will absorb some of the light, and depending on its composition, it will appear differently to us if it's got a lot of oxygen or a lot of nitrogen or hydrogen atmosphere. And this is the main way that we can learn about the what's going on with the planets themselves. What is in their atmosphere? Does it have an atmosphere to start with? Maybe does it even have clouds in the atmosphere? Are there molecular components of the atmosphere? And one of the things that we astronomers have been trying to do since the discovery of the first extrasolar planets over the course of the last 25 years ago or so is to look for planets that might have the conditions that we think of as being important for life. So one of the things that we would love to see is the evidence in the atmosphere of an exoplanet that the planet itself has liquid water on its surface. That is the characteristic of life on Earth, is that it's a water-based life. And it's also important to the history of the Earth that not only do we have oceans, but we also have land. You know, is there beachfront property, as it's said, on these extrasolar planets? And that's something that Webb will be able to see the evidence in the atmospheres of exoplanets that are rocky planets like the Earth. Does it have liquid water on the surface, or are their oceans completely frozen, or are they? Is it too hot for that, and too hot for liquid water? Essentially, if you look at our own solar system, Venus is too hot for life. Mars is too cold. All of the water on Mars is frozen, whereas the Earth is the Goldilocks planet that is just right, just the right temperature.
Well, those are some lofty goals and themes. And it's interesting because the organization that this podcast is sponsored by, the Association of Lunar and Planetary Observers, we're basically amateur astronomers who are doing some science. And
That's great.
Last year we just started our exoplanet section. So with the CCD imagers that are available now to the amateur, we're able to do light curves and analyze these possible exoplanets as well.
Yeah, absolutely. It is an area of astronomy that has just blossomed in the last 20 25 years. And when we first started thinking about Webb, we didn't think all that much about exoplanets because it was just a brand new field. By the time we sat down and wrote down the goals, the science goals for the mission, we realized that exoplanets were going to be important and included a chapter on planets and the conditions for life. But we kind of found like there wasn't a whole lot that we knew what to say when we wrote those goals down. And yet here we are about ready to launch the observatory. And something like 25% of the science program for the first year is going to be looking at exoplanets and disks and planetary systems. So that has become a very important part of our science program.
That is very, very exciting. And you mentioned one of the first goals was to look further back in time.
Mm-hmm.
How much further back will the Webb Space Telescope allow us to look?
Right. So the important thing is how close to the beginning can we get? So as I mentioned before, Hubble is able to see to detect galaxies that are emitting their light within the first 1 billion years of the Big Bang, after the Big Bang. That the Big Bang was 13.8 billion years ago. So we're looking back, 12 to 13 billion years back to within the first 1 billion. With Webb, we hope to take that back to maybe 400 million years, maybe as far as 250 million years after the Big Bang. But what's kind of more important is that it depends more on what there is to see than the capabilities of Webb itself. So when we find a population of galaxies that appear to us to be very young, just forming their first stars at these very great distances, and when we don't see anything that's any further away, any further back, that's when we can point to those galaxies that we are detecting and say, well, that must be the first thing that formed. There's actually two aspects to going further back. One is just that when things are further away, they're regardless of their intrinsic brightness, the apparent brightness gets fainter and fainter as you look at things further and further away. So we needed a bigger telescope than Hubble in order to go further. But there's another aspect to this, and that's brought in by the expansion of the universe. When the light is first emitted, the light from a young galaxy, from young stars, comes out in the ultraviolet and visible light regions, also in the infrared. But as those light waves travel through the expanding universe, they get stretched out. And so short wavelengths, blue light or ultraviolet light that starts out that way, over time, as it travels to us over the billions of years, gets stretched out and moved into the infrared. So Hubble has the ability to see a ways into the infrared, about wavelengths that are about twice as long as the wavelengths that we can see with visible light, the reddest that people can see. But that turns out to be not enough to see to these very early times. We have to go further out into the infrared. And that was a fundamental design characteristic of the Webb telescope, was to be infrared sensitive. Now, in order to do that, we have to make the telescope cold, because things that have a temperature will emit infrared light. And Hubble, which is at room temperature, emits light that will swamp the kinds of the signals from these very early galaxies that we want to see with Webb. So Webb is designed to sit behind a tennis court sized 5-layer sunshield that allows the telescope to cool down to a temperature of 225 degrees below zero Celsius. And that way, light, essentially the heat radiation from the telescope is not swamping the signal of the very, very distant galaxies that we want to see. So as an infrared optimized telescope, Webb can see further than Hubble can see, in addition to being able to see fainter things.
Yeah, when I was doing research on the Webb telescope, I was amazed at the size of the Sunshield. I don't think have we had another probe that actually had a Sunshield similar to this? I mean, not even the Parker Solar Probe has something like this, does it?
No, so this kind of very large, flimsy, it's kind of a plastic material called Kapton. It's got 5 different layers. Each layer, as I said, is the size of a tennis court, 22 meters on the longest distance. And it's deployed. We can talk about how we can launch something this big inside of a normal sized rocket. But it's a very large, very flimsy sunshield. Other missions have had sunshields, but nothing this big. No, so, for example, the Spitzer Space Telescope, which was an infrared telescope, kind of the sister of Hubble, the infrared sister mission of Hubble. Spitzer was a 0.8 meter diameter primary mirror, so a much, much smaller mission. It had a sunshield that would allow it to get to these very low temperatures, but Spitzer also carried liquid helium to cool it even further, which allowed it to get very cold, down to within I think 7 degrees of absolute zero. But with Webb, this is the first time that we have a very large deployed sunshield like this, and Webb is also passively cooled, which means that we don't have a big tank of liquid helium to keep it cold. We just allow the telescope to radiate its heat into deep space. And for the mirror and at least 3 of the 4 instruments, they're all passively cooled. The 4th instrument, the camera that works at the longest wavelengths, we have a closed cycle refrigerator that uses liquid helium to keep it, to get it even colder.
Okay. Well, most of our listeners I know are familiar with the Hubble. What would you say are some of the basic differences between the Hubble and the Webb?
Well, so the 2 biggest differences, as I mentioned, are that Webb is bigger. It's a 6.5 meter diameter primary mirror compared to Hubble, which is 2.4 meters. And that Webb is a cold telescope, infrared optimized telescope. So Webb's operating temperature, the primary mirror, is about 50 Kelvin, so 50 degrees above absolute zero. That's about 225 below zero Celsius. But there's also lots of other differences. In order to get Webb to be that cold and to have essentially a one-sided sunshield protecting it from the sun, we are sending Webb out into a deep space orbit, which is an orbit around the second Lagrange point. This is a special place in the Earth-Sun system in which the sun, the Earth, and the second Lagrange point are always lined up in a line. So as the Earth goes around the sun once per year, the second Lagrange point goes around the Earth once per year and goes around the sun once per year, and it always stays lined up. So we're going to put Webb out in orbit around that point. And so Webb's essentially in a solar orbit, goes around the sun once per year, keeping track with the Earth. In comparison, Hubble is in low Earth orbit, so Hubble goes around the Earth every 90 minutes. And what that means is that Hubble spends half of its 90 minutes on the daytime side of the Earth and half of it on the nighttime side of the Earth. So while it's in the sunlight side, it warms up, and while it's on the nighttime side, the Earth is protects Hubble from sunlight, and it will cool off. But because of that going in and out of the sunlight, Hubble has heaters on it that keep it at a pretty constant temperature. But that temperature has to be a warm temperature, essentially room temperature. So in order to have a mission that cools like Webb does, it has to be out in deep space. So it's a million miles away, 1.5 kilometers away at the second Lagrange point. That's another big difference that affects a lot of the mission. And then another thing that's very new for Webb is all of the deployments. So we're going to launch Webb in an Ariane 5 rocket. This is about a 5-meter diameter rocket, and the primary mirror is 6.5 meters. So we had to fold the mirror to get it into the rocket fairing.
It's actually 18 segments, I believe.
It's got 18 segments, 18 individual pieces of beryllium coated with gold that make up the primary mirror. The segments are each hexagons in a tile that is approximately circular with 6.5 meter diameter. And the two side wings, so 3 of these 18 segments on either side of the mirror, are folded back for launch. And so after launch, when we've gotten rid of the rocket and the fairing, and the observatory is on its way to the L2 point, we will do these deployments. And the first thing is to fold out this big 5-layer Sunshield. The Sunshield is kind of folded up around the telescope for launch. We do the front and back, and then pull out the sides on these booms and separate the 5 layers. The secondary mirror is also deployment. It's kind of folded up on top of the primary mirror. So then we fold out the secondary mirror and bring the 2 side wings of the primary mirror into the mirror plane. But we still have 18 segments at that point, and we have a long and very complicated process for aligning those 18 mirror segments to a common optical surface. It's not enough to just bring each individual segment into a focus, because that would not phase up the light. We have to go through a process of very, very precisely measuring using an interferometric type of process to bring those 18 mirror segments into a common optical surface and make sure that we have the best what's called a point spread function. If some of your listeners have their own telescopes, they'll understand what that means. But bring it into to have a good optical response over all 4 of the instruments. And that's actually a process that will take several months after launch. So when we launch towards the end of this year, unfortunately, it's going to be well into 2022 before we start to get good pictures and start to do the science. We have a plan for 6 months after launch. There's 1 month to get out to the L2 point and for the telescope and the instruments to cool down to the point where we can turn them on and start using them. 3 months to phase up the mirrors, and then an additional 2 months to try out all of the instruments, the 4 instruments, and all of their individual modes and filters and spectroscopy and all of that. So launch is going to be very exciting. And the first 2 to 3 weeks when we're doing these deployments will be very nerve-wracking. But even after that, it's going to be launch plus 6 months before we start to get the first science results out of the mission.
Yeah, having an engineering background, just thinking about the mechanics of controlling those 18 segments. And I have a hard time collimating one mirror in my telescope. I can't imagine what it would take to do 18.
Yeah, that's why it takes 3 months to do this. We have, essentially when we first turn on the telescope, we'll first turn on the camera, we'll point it at a bright star, and we'll see 18 out of focus images of that star. We can focus and align each of those images and stack them up, and then we have to do this more advanced process using what's called a dispersed Hartmann sensor to phase them up. Each of the mirror segments is controllable with 6 degrees of freedom. So that's the normal XYZ of moving around, but we can also tip the mirror, we can tilt the mirror, and we can rotate the mirror. Those are the 6 degrees of freedom. And then we also have an additional actuator right in the middle of each of the mirror segments that we can adjust the radius of curvature by poking the back and change that as well. The secondary mirror is also on a hexapod, so it's also controllable in 6 degrees of freedom. Altogether, it's well over 100 degrees of freedom that we all have to line it all up to work.
That's interesting. So you can poke the back. So what is the thickness of the segment?
So it's about, I'm trying to remember because I've seen some, it's about maybe 4 centimeters. Okay. We can't adjust it very much, but these mirror segments individually are polished to a surface roughness of 20 nanometers. Among the best mirrors ever made, as you might expect. What that means is that if one of these mirror segments were the size of the United States, the biggest mountain would be about 2 feet high.
My God. Wow. Yeah, I was lucky enough to be down in Redondo Beach for some of the I got a tour of the facility where the telescope was being built, and so I was above the clean room, being able to look down and see. I was amazed at the size of this thing.
It is huge, and I don't know if we've. I'm sure we've never put anything this big in deep space. It's the International Space Station is bigger, but there's not very many things that humans have put in space that are bigger than Webb, and certainly it is one of the biggest in a number of different ways of measuring it. It's one of the biggest science projects in the history of the United States and the history of the world, in terms of like the number of people working on it, the amount of effort that went into it. In terms of mass, it's only about half the mass of Hubble, the whole observatory, because one of the things that we get for having the 18 mirror segments is that it is much lighter. It is much less mass than a solid piece of glass would be, that would be 6.5 meters in diameter.
True, and just the technology and the challenges of building something this complex. I mean, I'm sure there's international collaboration with this as well.
Yeah, there is, and in fact, Webb is a joint project of NASA and the European Space Agency and the Canadian Space Agency. So tripartite project. that was negotiated very early on in the project in the late 1990s. The international collaboration was put together. Nominally, the European Space Agency is a 15% partner, and the Canadian Space Agency is a 5% partner. So, NASA is the lead, but the Europeans are contributing essentially 1.5 of the 4 instruments. So the European Space Agency is built the near-infrared spectrograph and worked with the United States on the mid-infrared instrument. And in fact, they built a lot of the hardware, the optics, and for the mid-infrared camera. The United States contributed the detectors and the cooling system for that camera. And then the Canadian Space Agency is contributing one of the 4 instruments, which is a specialized instrument that does that's kind of designed to do particular things very well. One of which is to study transiting planets around very bright nearby stars. So that's one of the most exciting parts of the mission. And then another contribution by the European Space Agency is the rocket. So it will be launched on an Ariane 5 rocket.
That's a very dependable rocket.
Yeah, it's we've had well over 100 Ariane 5 launches in the past, and they've all done very well. So Webb will be heading down to South America because the Ariane 5 is launched from a spaceport in Kourou, French Guiana, just north of Brazil, on the South American Atlantic coast.
Okay, so you mentioned that it's still in Southern California being assembled. What is its current build status?
So it is fully assembled. We have gone through the final in what's called environmental testing, which is essentially a simulation of launch in terms of the vibration and the acoustic, the noise of the rocket. So the observatory is fully assembled. We put it on a shaker table and just literally shook it up and down.
That is one of the scariest tests I ever witnessed on any spacecraft.
It absolutely is, to see that, to see this very high-tech, very delicate, expensive scientific instrument being shaken up and down. But that's what we have to do. We have to simulate the rocket ride, and then do a final checkout of everything after that vibration test. And then also we blasted it with noise. That is, again, what the level of noise that you would get inside the Ariane 5 rocket. So we've gone through that. We did a final deployment test of the Sunshield, and we've just finished folding the Sunshield back up. So the 5-layer membranes are all folded up. The next step is to do all of the attachments to make sure that those Sunshield membranes don't slide around. And then we'll do a final deployment test of the wings of the primary mirror, pack it up into the shipping container, and by late summer, and send it down to Kourou, where there's sort of 2 to 3 months of processing down there to get it into the rocket fairing and ready for the launch.
Good. Do you have a target launch date? I know that's always getting shifted to the left.
So it's October is the goal for the launch. That's what we're aiming at. Launch in October. We don't have a day yet, but should be sometime in October.
Are you going to be there?
Launch date. That's an open question. There's not a lot of room for people that to be there. So we don't. Unlike a launch out of the Kennedy Space Center,
Jonathan,
in Florida,
it's your baby.
I know.
So you got to be there.
we've got a lot of the action going on back here at the Operations Center, which is in Baltimore on the campus of Johns Hopkins. And COVID's also, impacted what we can do. So we haven't worked out who is actually going to be at the launch site and who's going to be at the Operations Center. The action's happening actually at the Operations Center where we
but sure there's nothing like seeing your baby take off.
There is. We'll see. We'll see.
I hope you get to do that. That's very exciting.
Yeah.
Yeah. Great. Now, is there anything else you'd like to share about the Webb telescope?
Let's see. So one of the things that is just hot off the press, just brand new news, is that we have selected the first year of science observations. Oh. So when we planned this telescope back in the started to thinking about what it would be built to be able to do back 20 years ago, we always knew that we would want to adjust what it actually does based on following up on the most recent results from Hubble, from ground-based telescopes, the most exciting exoplanet targets, and the studying galaxies that have been well studied with other telescopes. So the way we choose what the telescope will actually look at is through peer-reviewed proposals. So the worldwide astronomical community, astronomers from everywhere, submitted proposals in late November, and those proposals were read by a panel of almost 200 scientists were involved in the peer review, and the very best observations were chosen for the first year. And that suite of observations was just announced last week. I'm excited to personally be involved in 3 of the 220-something proposals that were selected. And in all, there's 2,200 scientists involved. Either some of them were the principal investigator, the lead author, but lots of large teams involved in some of these projects, because it's just going to be such a very rich data set that there's going to be lots of interpretation that needs to be done from the observations. So that was very exciting, the selection of the first year of observations. And there are, it does cover just about every aspect of astronomy, from our own solar system, the outer solar system. Webb can't point towards the sun. So Mars, Jupiter, Saturn, and a lot of work actually in the very outer solar system, the Kuiper belt, which includes Pluto, but has lots of other small dwarf planets that we think kind of hold the pristine original composition of the dust cloud that formed the planets and our sun 4.5 billion years ago. So everything from our solar system out to the very edges of the universe, the looking backwards to just to see what we can see in the very within the first billion years after the Big Bang, and lots of work within our own galaxy and nearby galaxies. It's just going to be a whole lot to learn. What I would say, although I'm very excited to be involved with some of the projects on galaxy evolution myself, what I think is going to be the most interesting thing that Webb will do is probably something that we don't really know yet what it's going to be. Some kind of, we're looking at something and it doesn't match what we thought it would look like. We'll be making new discoveries that are unexpected. And I think that's kind of the most exciting thing That's certainly been true of Hubble. If you take what people think of as like the top 10 results or top 20 results from Hubble, less than half of them are things that people predicted before the launch, before it was launched, and the other half are things that just kind of came out of nowhere and surprised the astronomers.
That's why we do what we do.
That's why you do observations. If you could predict everything, then you might as well just be theorists and you don't need observations.
That's right.
So
that's right. Now, when the telescope does become operational, will professional astronomers be able to book telescope time on it?
So that's this process that I was talking about.
Okay.
They write proposals.
Okay.
They ask for the amount of time that they need, and the proposals range from, very small, just a couple of hours, all the way up to I don't know what the biggest one is, maybe 200 hours in the first year, and they justify that by making the predictions of what they'll see, and also indicating where there's things to learn. These proposals are read by the peer review, and the best ones are chosen, and that's going to be an annual process.
Oh, great!
So we've worked out the first year, but about 4 or 5 months after the start of science operations, so we've got 6 months to commission the telescope, get it going. We start doing the science observations. About 4 or 5 months after that, we'll have the call for the second year of observations. Okay. And that will happen every year. And that allows us to do follow-up. So with a discovery in the first few months of the mission, astronomers can then write a proposal to do follow-up. Maybe they see something in a picture, in an image, and say, well, let's break the light up with the spectrograph and get more information about these objects. Or maybe it could be that somebody finds something with a ground-based telescope or with Hubble, and that also justifies following up with Webb to get more information about it. That's an ongoing process every year through the lifetime of the observatory.
Okay. Well, I was excited about this before, and now I'm really excited.
Yeah.
Good job. Wow. What is the estimated lifetime?
So the lifetime, that's an interesting question. There is one thing on board that would eventually run out, and that is fuel. The mission, the spacecraft, uses fuel, not a whole lot, but uses some fuel to maintain its position in orbit. The second Lagrange point is not a stable orbit. It's a semi-stable or metastable. It's not, essentially things will drift away. So it's, and Webb is actually in kind of orbit around the point anyway. So to maintain its position in space and not drift away from the Earth, we need to use fuel, probably firing the thrusters about every couple of weeks or so. And then the other thing is that it's also necessary to manage the angular momentum of the observatory. The Sunshield acts like a solar sail. And when we tilt that, relative to the sun, it's going to build up angular momentum. And that's another thing that we need to use the rockets to dump that angular momentum. So that is the one thing that could potentially limit the lifetime. Now, so obvious question is, how much fuel do we have? And we've got a requirement for 10 years of fuel. There is margin on that, which means we've got some extra just in case. And another interesting thing is if we get a good launch, if the rocket works well compared to what we expect, then we don't need to use as much of that fuel as if we as if something is a little bit off with the rocket. And that translates into additional years of lifetime. So that's one of the things that astronomers will be really interested in on launch day is how well did the rocket work at inserting it into the orbit that we want, and how much fuel do we have to use in a couple of planned corrections that we have on its way to the L2 point. So that translates into lifetime, additional lifetime. So it could well be that the fuel lasts much longer than 10 years. And at that point, it then becomes just how long it will keep working.
And funding.
Well, so NASA's not going to turn this thing off. Just like NASA is not going to turn Hubble off.
Right.
As long as it's working, as long as it's producing good science, it's a high priority for the agency, and the funding will continue. So I don't think, that's always a reality with a lot of projects. But Hubble has been incredibly productive. It's 30 years and counting, and it's still doing really good science.
Right.
Hubble also has a peer-reviewed proposal process,
right,
and also and astronomers are still very eager to use Hubble and submit many more proposals than it's possible to than there is time to actually carry out. So we're not running out of things to do with Hubble, and we won't ever run out of things to do with Webb. And I think as long as it's scientifically productive, the funding will be there to keep the operations going.
That sounds great. Now, one more thing. I was reading your bio, and I see that you're a guitar player.
Yeah, that's a hobby. My wife and I play folk music, what's called fiddle tunes. And the name of our band is Transatlantic Crossing. I actually, as I mentioned, I was in England for 4 years, and that's where we met and got married. And we met in a folk group. It was actually a dance group, but it had an associated band. And so we do traditional folk tunes of the British Isles, the England, Ireland, and Scotland. And then we also play what that folk music became when people brought it over to the United States. So sort of like New England contra dance music and Appalachian music.
That's great.
It's fun. So, it's good to have a hobby.
Oh,
as well as a job.
Oh yeah, no, that's great. So do you do concerts and things like that as well, or?
We've played for dances with folk dance groups.
Okay.
And like for example, under COVID, there's not a whole lot going on,
right,
but my wife and I just sent an email to the neighborhood email list and said we're going to be out on our porch on St. Patrick's Day playing Irish tunes, and
how fun.
A bunch of the neighbors came around and spread out, all socially distanced. So that was fun. Yeah.
Oh, that is great. That's good. Yeah, fantastic. Well, Jonathan, this has been really informative, really entertaining, and I want to thank you for coming on the podcast today.
Absolutely. My pleasure. It's been fun to talk to you. And I hope all of your listeners are going to be watching when Webb is launched. And then 6 months later, when the pictures and the science results start pouring in.
Yeah. Thank you very much. And good luck on launch and the mission.
Thank you.
Well, that'll do it for this episode of the Observer's Notebook podcast. I again want to thank Dr. Jonathan Gardner coming on the podcast today and talking to us about the James Webb Space Telescope. What an interesting topic, interesting project, and a great interview. Thanks a lot, Jonathan, for coming on. We upload a new episode of the Observer's Notebook on the 1st and 15th of every month. You can subscribe to us on iTunes. If you do, please rate and review us. I really appreciate it. And you can also listen to us on Apple Radio, iHeartRadio, SoundCloud, Spreaker, Google Play, Stitcher, and that annoying box that sits in your house, the Amazon Echo. You can help support the podcast by donating to it via Patreon. You can give up to $35 a month, where you will receive 1 year's membership to the ALPO and producer credits on the podcast. And with that, I'd like to thank the producers of this podcast, Steve Siedentop and Michael Moyer, for their generous support of the Observer's Notebook. Thank you very much. The link for Patreon, as well as the link for the ALPO, is in the show notes. You can contact me via email at cometman@cometman.net or on Twitter at ObserversNBPod. Until next time, my hope is you always have clear and steady skies. Thanks for listening.